and dark energy, but it will not be, rigorous. It will not be really involve calculations. It will be just like a bedtime story for you. And if you are interested more, then there will be, much more in the exploration in particle physics and in the explorations on cosmology. But explorations in particle physics mostly about dark matter and dark energy. So if you are interested more, go to those, attend those courses. So I'll basically tell you, why we think there is dark matter, and at least one reason why we think there is dark energy. So why do most cosmologists believe there is dark matter? And the story goes, quite long back in time, because already in 30s, actually, there were first indications that it must be so. So if you go back to 1930s, there was this amazing person, Fritz Zwicky. So the story goes that this person couldn't get along with anybody, right? So he was basically, fighting with everybody. But he discovered lots of good things. So he's still a very, very good person. Okay. And so what he did, he studied clusters of galaxies. Clusters of galaxies. So what is a cluster of galaxies? So it's basically a group of very many galaxies. So the average distance between them is, let's say, r, and then each galaxy has something like an average mass m. So and so they are sort of moving, and average velocity of these things is v. So cluster of galaxies is a statistically steady spherically symmetric, basically spherically symmetric self-gravitating system. Self-gravitating system. And let's say we have n objects, so of big N objects, in this case galaxies, and they have average mass, so m, average is m for each galaxy, and average orbital velocity, and velocity v. Okay, so this is what he studied. And so because, this is like a statistically steady system, you can apply so-called Virial theorem on these things. So you just take Newtonian gravity and you apply Virial's theorem, which tells you what is time average of the kinetic energy and how it is related to the time average of the potential energy of the system. So now the total energy is 1/2. We have n objects, m v square, okay, because each object has velocity v approximately. The potential energy is just, I take any combination, so I say that, each galaxy is approximately distance r from any other galaxy. Okay, so it's minus 1/2 n times n minus 1 g Newton m square over r. So that's the total potential energy. And then the Virial theorem says, and again, you can look it up in Wikipedia if you don't know what this is, that an average E is minus U over 2. And that basically comes from the scaling properties, how U scales and how E scales. It's also nice to discuss in Landau and Lifshitz if you're interested, the first volume mechanics. So what it means is that the total dynamical mass of the whole system is m, which is n times small m. And then I can express that, so if I just equate these two equations, and of course it depends on v and depends on r. So it's 2r v squared over g Newton, which if you plug what he measured, then you find that it's 10 times m luminous matter. Okay. So basically, you can estimate, well, you see something shining, and that has this mass luminous, but the dynamical mass, which is according to the Newton's law, is actually 10 times bigger. So actually, lots of mass is hiding from you, and it's not shining, right? So that was the first indication that there might be something like dark matter in the universe. Okay, so that was 1930s here. By the way, this guy was, as I said, he was very good. So a few years later, he even proposed that you can perhaps measure dark matter by the gravitational lensing. So if you observe, very distant, very bright things, for example, like quasar, right? So if you observe a quasar and then suddenly a galaxy is containing the dark matter, swipes in between that quasar and you, then of course the light gets lensed, and so you see the enhancement of the brightness of the object. And so he proposed this in 1930s, and actually now I think recently this has been measured. So really he was a very, very good guy. Okay, well, he wasn't a good guy, but he did lots of good stuff. So this is 1930s. But I would say the overwhelming evidence was due to 1970s, and a person, Vera Rubin, I don't know which nationality she's from. So she studied galaxy rotation curves. So what I mean by that, so if you imagine you have a galaxy here, and it looks something like this. Okay. It almost looks like a Japanese weapon, but okay. But anyway, so stars here, but you can have also a few struggling stars here. Okay. So here, a few struggling stars. And so what she did is that she measured, how fast they basically move around the galaxy. So she measured the velocity v of how fast these struggling stars, very, very far from the center, actually, how fast they move. And so, again, doing very naive Newtonian calculation, you would think that the Kepler's law gives you or the Newton's law gives you that centrifugal force equals to the gravitational pull. So now, if I'm outside of the matter, if all the matter is included, this is just a constant, and it equals to the total mass of my system, right? So that means that outside matter V must behave like 1 over square root of r. Okay. So this is what you would expect once you are outside of all the matter there is. Then V must behave like this, where R is, of course, the distance to the origin. Okay. So now, how that would look like is, so if I plot V, and then I plot R, so you would expect that goes something like this, and then there's this square root of R follow. So here is up to, I include more and more matter, so I'm just picking up more and more matter, but the last visible R, so it's R of visible light or stars. Okay, so I can see matter only up to this distance, so I'm increasing the amount of matter I have. But then once I'm outside of the matter, this is the fall off, which is predicted by Newton's law. Okay, so that's the prediction, theoretical prediction. But what she actually measured was this thing. Okay, so obviously it is not falling off. It seems that there is still some much more matter contained in your galaxy than you can actually see. And so that was the evidence. And again, the galaxy contains much more matter, and the matter it doesn't go only here, but it goes even further away from that galaxy. Okay, so that is like overwhelming evidence that that's where really people thought, well, there is some hiding matter. Okay. So now, interesting question is whether this hiding matter can be, normal matter baryons, which is just not shining enough, so that we don't see it. Okay, so that's the question. But the truth is that you can show, and I will try to hand wave, that dark matter is not baryons. Okay. So really the question is, can it be a normal matter, but just too dark, not so shining, not having enough temperature so that we can see it now? So for example, matter which is not contained in stars, but it may be like distributed around the galaxy or whatever, something like plasma or whatever. Okay, but so one evidence that this is true is already what you know is that, well, is this Big Bang nucleosynthesis, BBN. And so I tried to show you yesterday that, how many, what is the abundance of various elements depends on this parameter eta, right? So eta, which again is the number of baryons divided by number of photons, which is 10 to the minus 9. And, it really matters what this eta is. If you start moving, you start probing what would happen if eta were different, then you get completely different prediction for the number of helium and so on. Okay, so now what I will try to, well, you just have to believe me. So now this eta parameter is conserved in time, is conserved. So basically, BBN happens like 3 minutes after the Big Bang. It's already relatively low energies, so you cannot really, mess with the baryon number, right? So number of baryons is conserved. Standard model, predicts that. So you cannot. But also you have, this incredible amount of photons, and so if you produce some more photons, it doesn't really matter. So because it's 10 to the minus 9, then if you produce 1 million more photons, it's still okay, right? So this eta is conserved, which means that whatever eta was at the time of Big Bang nucleosynthesis, it must be the same now, right? But what you can measure is, so now we can measure, or we measure n of gamma. So we measure the density of CMB, right? We can measure how many photons are there. So this is given, this is fixed by BBN. So that means that we can calculate, so predict n of baryons today. Right? I can measure what this guy is now. I know what this is, so I can predict what n of baryons is now. And then if you look at the sky, it's precisely all the shining baryons we see in the stars and galaxies and so on. So, and so from here you conclude that all baryons are the shining matter. Okay. So from here you conclude that really dark matter is not baryons, which I think is quite an interesting conclusion, right? Of course. But you are already at very low energies. After BBN, you are very low energies. So you don't expect any departures from standard model, right? Yeah, but here you are talking about, there is 30% of dark matter, and there is 5% of baryons. So it's, hundreds of percent or whatever. Okay. So another, if you don't like this explanation, then I will not explain here anything. I will just mention that this is true. So again, if you study the CMB thing, then it provides an independent measurement of, what is the composition of the universe. And so during recombination, so I draw that picture that we have this plasma of electrons and protons and photons and so on. But of course, and which I didn't draw, is that we have to have this dark matter already then, because we had it. We had it here, so we have to have it here as well. So we have dark matter, but that dark matter is sort of decoupled from the rest of the plasma. So it doesn't really, play with the plasma. So what it means is that, so during recombination, you can basically split your matter content into two things, which is the plasma, which is the baryons and radiation, And so these guys, they have pressure, and of course it self-gravitates with a gravitational self-interaction. And so if you did any course on plasma physics, then you'd know that then the plasma must oscillate, basically. Okay, so then there are oscillations. Okay. So basically, if you want to squeeze the plasma, so because it's, it's these electric repulsive forces, then it wants to spread away, but also, there's this self-gravitation, attraction, so there's a characteristic vibration in the presence of, gravity, and because the plasma is basically charged. So you have characteristic oscillations of plasma, but at the same time, you have this dark matter present, and that dark matter is completely decoupled from the rest. So it basically doesn't contribute to the pressure of plasma, but it is gravitating, right? So it has mass, and because it has mass, it's also gravity. So it produces gravitational potential well. Okay, so it basically changes these characteristic oscillations because it adds more gravity. Okay, and so that's why. So now you can play with this. So how much dark matter I have to have? How big this gravitational potential well I have to have in order to produce what we observe, right? So this is the CL picture, and then you have the first peak and the second peak, third peak, and so on. So it's the first, the third peak. I'll talk about these next week a little bit more, but not too much more. Again, it'll be your explorations in cosmology. I'm just giving you the overview. Third. Okay. And so really, what this displays you is basically what the oscillations of plasma were at the time when the CMB was released. Right? So the plasma was oscillating, it was the photons were captured, and it was like a perfect blackbody cavity or whatever. And at some point, the reactions, the Thomson scattering stopped, and suddenly the photons could roam free. But they basically carry the information about the oscillations of plasma at the time. Okay, and that produces exactly these peaks. And then just a statement from nowhere. So the position of the first peak basically gives you how much total matter you had. So how deep the potential well was at the time when this was released. And that fixes that to 0.3 approximately. And then the ratio, the first one and the second one, so the ratio of amplitudes of second and first peak fix that omega of baryons is 0.05. Okay, so this is, there are programs where you can actually download from internet, and you can play with how much matter you put here and how much plasma you put there, and then it produces different pictures of CL, right? So you can play with it yourself. Just Google CL and do it yourself or something like that, and you can really observe these things. How the picture changes when you put different amount of dark matter and when you put different amount of plasma, and so basically you can read the content of the universe from this CL as well. Okay, and again it points to the fact that you have dark matter. So I would say this is overwhelming evidence is that first CMB but also BBN, they are sort of independent indications that you have dark matter which is not baryons. Okay? So then, if it's not baryons, what it is? So what is dark matter? And the answer is nobody knows. And there's Nobel Prize waiting for you there. So we have several possibilities, however. But before I go to these possibilities, let me just stress that basically all the evidence we have for dark matter is the gravitational evidence, right? So here I'm just using the Newton's law or the virial theorem, which is based on Newton's law. So it's based on gravity, that observation. Here, again, I am interested in gravitational potential well, right? So again, I'm probing basically gravity. So far, let me just stress that. So at this point, only evidence for dark matter is gravitational. So when you are doing research for your Nobel Prize, you better be aware of that, right? So maybe you can mess with gravity and everything will be fine, and maybe you don't need dark matter at all. Okay, so we have the following possibilities. So So one of them is that GR is wrong. And there's lots of people at Perimeter who is actually trying to work on this possibility. And so, for example, a massive gravity would be an alternative to Einstein's gravity, but it has so many problems that, yeah. So until very recently, it was completely hopeless. And then former postdocs at PI, Claudia Deram and others, actually they made it sort of more attractive because they solved some issues of the massive gravity. But I still don't think it's actually, you know, it still has problems. The theory still has problems. But anyway, so that's definitely one possibility. The GR is wrong. You know, at the point of galaxies, you can, so there's like MONDS, which is like modified gravity theories, and it's like ad hoc modification of gravity so that the galaxy rotation curves come out right and so on. But at larger scales, it has problems, and you cannot really, you know, do it. But you know, maybe the massive gravity or maybe some other forces. Yeah. So anyway, this is a possibility. GR is wrong. And then the other possibility is that really we have dark matter. And there's two main categories of dark matter. So the first category is called machos, which stands for massive compact halo objects. So that's the first possibility. And then the second possibility is WIMPs, which stands for weakly interacting massive particles. So basically what you assume in the first category, you think that you have some, you know, relatively large objects which can contribute to this dark matter. In the second category, you assume that you have some fundamental particles which are nevertheless massive. And so if you have lots of them, then they can produce the dark matter you want. So now the first possibility, the machos, actually seem rather unlikely at this point. So if you had objects, for example, typical object of which would fall into the category of machos is a black hole. So if you had like small black holes and you had lots of them, right? Then they could provide you, you know, dark matter. So, but because they are microscopic objects, then could be observed again by gravitational lensing. Microlensing. So the same thing as what Zwicky was suggesting is that, you know, you observe your favorite star and you look at its intensity, and then if that black hole gets in between you and that star, you see an increase of intensity. Right? So this is what you would see. So I'm looking at my favorite star, and at some point, you know, the intensity magnifies. Of course, it's because if you're looking here, and this is your star, and at some point there is your dark matter, you see all these things coming to you, and that's why the intensity is actually bigger. Well, let's skip the picture. But anyway, so intensity magnifies. Okay, so dark matter in front of your So now people have been looking at this possibility, and so there are really people who observe their favorite star for a long time and measuring its intensity, but so far nothing. Okay, so far no observations, and so it gives you a constraint on what type of how much mass this thing has to have. Which is ruled out. Okay, so from these observations, you know that mass is in between 10 to the minus 8 solar mass to 10 to the 2 solar mass are ruled out. So if you had black holes, which really were dark matter, then they cannot have masses within this range. Okay, so now it is very unlikely that your black holes would be more massive than 10 to the 2 solar masses, right? So then you would probably, it's very unlikely. It's possible that they are actually smaller than this. So this is approximately the mass of Pluto. So if you actually, so they can be smaller than Pluto, right? Okay, but you have another condition. So if they were really black holes, then you know that black holes do Hawking evaporate. And so they evaporate faster if they are smaller and smaller, right? So if you had black holes, which would be 10 to the minus 19 solar mass, they would already Hawking evaporate. Black holes would already Hawking evaporate. And moreover, they would change our vacuum, right? So they would enhance the change of vacuum. So probably our universe would be different. So this is also not possible. So you have something like a window between 10 to the minus 19 to 10 to the minus 8, which is still a possible window. Okay, so there is still a window. So these black holes, because they are so small, and they wouldn't be formed like a collapse of a star. So typical black hole is formed as a collapse of a star. Well, you have three sizes of black holes. You have very, very small black holes, which would be these guys. These are called primordial black holes. Primordial. Because they are small. Then you have typical black holes, which you observe in our universe, which were formed by a collapse of a star, which is approximately, let's say, mass of the sun. And then you have these supermassive black holes at the center of galaxies, and nobody knows how these are formed, because people observe them quite early in the universe. And so there is a theory how quickly the black hole actually can form if it was formed by accreting matter. So let's say I form a small black hole, and then this black hole likes to eat everything which is around it, right? So it's getting bigger and bigger because it's consuming more and more mass. So now there is a limit, reasonable limit, which is called Eddington limit. It says, how fast I can become a big black hole. And so those supermassive black holes, some of them actually violate this bound. So they are observed very, very early in the universe, but they are very, very supermassive. So they violate this, accretion possibility. So nobody knows how these are formed. But anyway, so this is another third kind of black holes. They are primordial black holes, very, very small black holes, which can exist between these 10 to minus 19 and 10 to minus 8, and it's a possibility. But the problem is that, for example, if you look at this thing here already the dark matter had to exist. But this is like 3 minutes after Big Bang, right? So you would have to form these things really, really early in the universe. And again, the question is how you form them, right? So, so it's possible. So there's still a window, possible, but unlikely. It's not a statement, it's a question mark. Okay. So that's about machos, and you will probably hear about them more in your exploration course. So now let me say a few words about WIMPs. So now we have again several possibilities. for WIMPs. So one possibility is that they are so-called thermal relic. So what it means is that they were at some point far, in the past, they were part of your plasma. Okay, so was originally in thermal equilibrium is the rest of matter. And only, after some time, they decoupled from the rest of the matter and became sort of independent and not coupling to ordinary matter. Okay, so that's a great idea. So now we have two possibilities. So one of them is that when the dark matter particles decoupled from the rest of the matter, they were still relativistic or they were not. Okay, and so you have either hot thermal relic, which means that decoupled when it was still relativistic, so at the time when it decoupled, the mass of that quantity was much smaller than the temperature of the plasma, and cold, where it wasn't, where it was already non-relativistic. Okay. So now, typical example of the hot thermal relic would be something like neutrino. We know that neutrino is very, very light, so it's likely that if it were the dark matter, as I will show you immediately, it cannot be, but let's say it is. So if it were, then at the time of the decoupling, the mass is much smaller than the temperature. Typical example of cold is for example, lightest supersymmetric particle LSP. And so what is question?
Yeah, so the standard one of cosmology is CDM, right? CDM. So
okay, very good. Thank you for that. So very good. First of all, I will show you that you cannot have hot thermal relic, that it actually, you can exclude it based on very simple calculation. I'll show it in a minute. Yeah. Yeah. But it's a possibility at this point, right? So, but for this to have cold, you need, for example, like supersymmetry. You need more interesting things, okay? But what is very attractive about this cold thermal relic is there is something which is called WIMP miracle. And I will not say anything about it because you will probe it in your homework. Okay, so now I'm not lying with WIMP miracle. See homework 2. And one of the questions is why this is a miracle, so I will not really say anything about this. But something which is sort of like very, very natural, right? So cold thermal relic is quite attractive possibility. So that's thermal relic, and finally you can have non-thermal relic. So that means it was never part of equilibrium, and you have possibilities like axion. And again, I will not tell you anything about this because this will be part of tutorial 4. So look forward to Thursday's tutorial where you will probe the possibility of having an axiom as a dark matter candidate. Okay. So let me now show you that really we cannot have hot thermal relic. And the reason is that if the dark matter was still relativistic when it decoupled from the matter, then you can place a bound on the mass of the particle. And that mass of the particle would be too small. If it were too small, then, for example, when you observe your CL for the CMB, then this gravitational potential well wouldn't, behave very nice. It would be too low gravitational potential well, and so CMB would look like completely differently. So if dark matter particles are too light, they wouldn't produce the right gravitational potential well, and you can rule them out based on this CL. So that's the idea. So let me place the bound. Let me show you what the bound is on the mass of this hot thermal relic by doing very simple calculation, or more like an estimate. Right. So hot. So let's say that I have a particle chi, it's my dark matter particle, and it has this mass m chi, and this must be still relativistic when it decouples. So that's the assumption. So now it freezes out at some point, and then after that it never couples to any matter anymore. So from freeze out till now, the following must be true. So the number of these particles chi is preserved. So it goes like 1 over volume. And the entropy also goes like 1 over volume. Entropy density goes like 1 over volume. So you have m chi over s at the time of the freeze out must be the same as m chi over s now. Okay? So this must be true. So from here, you have that m chi now is m chi at the time of freeze out as 0 over SF. Okay. So now we know something. So we, for example, know what S0 is. So where? So S0 is basically given by, the photon mass now. So it's G as 0. So I'm just using these thermodynamic formulas, which are like 2 lectures ago. 2 pi squared over 45. And this is the temperature of CMB now. And GS is the effective number of relativistic degrees of freedom now, which is approximately 4. Okay, so that's that. So now n chi at the time of freeze out, because the matter was still relativistic, I can use the relativistic formula for n. Okay, which is the number of degrees of freedom of that particle times this zeta function of 3 pi squared Tf cubed. And the entropy density at the time of freeze out is G as freeze out 2 pi square 45 TF cube. Okay. So now if you look at these things, so the particle density of this particle now, so now if you look at this guy, and this guy, then you have TF cube over TF cube, so TF gets cancels, and you don't need to know it. So it's proportional to T0 cube, and then something you already can estimate or approximately know, right? So today, dark matter is cold for sure. Which means non-relativistic. So if I want the density of this dark matter now, it's just given by m chi times the particle density, m chi 0. And from what I told you, this must be m chi and T0 cube. I'll use the explicit formula, but TF cube cancels if I use that formula, and then there are some factors standing in front of this, which we'll have to calculate in order to get the estimate. But this is definitely true. Okay. So now this ratio to critical density omega, it's just rho chi 0, rho critical now. Well, it's this thing divided by whatever the critical density is now, which I can read from the Hubble expansion rate now, okay, from the Friedmann equation. So this is m chi 0 divided by, I'm using the Friedmann equation, so it's 3h0 square over 8 pi g Newton, and g Newton I just write m Planck square. Okay. So now, if you plug everything here, what you get is, well, I don't have space, so you don't get anything. So this omega chi 0 is, well, the number of relativistic degrees of freedom of the particle chi, which is, let's say, 2. It has spin 2 particle, spin 1 particle, divided by the number of total the degrees of freedom at the time of freeze out, which you can sort of estimate, let's say 100. Okay. 8 times 10 to minus 2 divided by h 100, it comes from big H, and then m chi over ED. If you plug in the things like, well, okay, so now the number of effective degrees of freedom is something like 3.91. The Hubble constant now is something like 2.13 times 10 to minus 42. This is your uncertainty in the Hubble constant, 0.67, and GeV. M Planck is something like 10 to the 19 GeV, and T0 today 3 Kelvin, which is 2.35 times 10 to minus 13 GeV. Okay, so then you get this beautiful formula here. Okay, so now this fraction here, so this guy here, well, if I have 2 degrees of freedom, this guy is 2. Let's say I have, if this happens very early in the universe and then all particles are still relativistic, this is something like 100, right? So this thing, you know, it's 1 over 10 or something like that. You know what this guy is approximately. So then basically it gives you the mass in chi if you know what omega chi 0 is. But you know what omega chi 0 is. If all dark matter were this particle, then you know that omega chi 0 is something like 25% of the universe, right? So since omega chi 0 is something like 1 over 4, then this is smaller or equal than 1 over 4. I said this is something like 1 over 10, and it gives you an estimate for m chi. So from here, you conclude that m chi is smaller than 10 electron volts. So from this crazy calculation of a crazy estimate, you realize that if, you know, at the time when the dark matter, you know, decoupled from the matter, if it was still relativistic, then the mass of that particle must have been you know, that small. This is really, really tiny mass. Okay, and the statement is, which I am not going to prove to you, but if that light then CMB would be ruled out. Simply, you know, the dark matter wouldn't produce the correct gravitational potential well, so that you would observe the CL as you observe it today. Okay, so this basically shows you that I couldn't have dark matter which would be relativistic at the time of decoupling. So that's why the cold dark matter is probably the most likely possibility. But, you know, another possibility is that non-thermal relic you have, and as I said, you'll study this in your tutorial 4. It's possible. It doesn't give you a miracle like here. So miracle means that, you know, something really is very, very natural. And so, you know, it's likely that this possibility is right. Here, you get a calculation, you get some estimate, but it's not a miracle. Okay, it's something which is possible, but you know, it's not something you would expect. Yes?
What about the inflaton? Could that be somewhere in this list?
Well, inflaton is like a scale field, if you want. Inflaton, well, okay. Okay. Well, inflaton is definitely here all the time if there was inflation at the beginning of the universe, but you just assume that it's too heavy to excite it. So now, I don't know if it could contribute to dark matter. Well, the idea is that you basically change all the kinetic energy of the inflaton into the heating your blast of particles so that you produce your hot Big Bang, right? So that's the idea. So now that means that the only potential energy would be left, and you would have this supermassive particle, but I don't know if you can excite it. So it's a good question. I don't know. Yeah. But yeah, okay. But these are the standard possibilities. Of course, my favorite is black holes because I study black holes. But unfortunately, they are probably ruled out. Okay. We have time. We don't have time. Okay, maybe I can just say 3 words about dark energy, and we can do the calculation tomorrow. So if this was part E, then we have part F, which is dark energy. Okay, and so again, I'll try to give you like two simple arguments why people think there is dark energy. And again, if you are interested more, you can attend other courses. So, but already in 1980s, people thought that something is fishy. And the reason is that if you look at your Hubble's equation, h squared is 8 pi g Newton, 3 rho. Now let me separate this curvature component k a squared, and then let me put the lambda separately as well. So now this will be just rho of matter. And you also know that rho critical would be like 380 squared over 8 pi g Newton. So now what people observe, so they haven't thought about lambda, right? So they thought that lambda is not there. And then, so what you can do is that by measuring H0, you know what rho critical is, right? So if you know what rho critical is, you can determine what K is, okay? So, okay, measuring rho critical and measuring rho, well, which you see the components of the matter. So for example, the dark matter plus the normal matter, right? Then you can say what K is, okay? So measured rho, which was rho matter plus rho dark matter. Okay, rho baryons plus rho dark matter, and they found that it's something like 0.3 rho critical. Okay, so this was the measurement. So if this is true, if rho is smaller than rho critical, then you would find that, so if no lambda, then you would find that K must be -1. That's the curvature of your universe, -1. And so now you find the age of the universe from the formula I gave you, like second lecture or whatever. So if this were true, then the universe would be T, which is something like 8 times 10 to the 9 years old. Okay, so this is the age of the universe, that's small t. And so if K were -1, I had only rho, which would be consisting of baryons and dark matter. Then this would be the age of the universe. Okay, so that's a very nice prediction coming from cosmology. Now, astrophysicists would confront that with their observations, but at the time, it was obvious that they observed some globular clusters, which actually were much older than this. Okay, so astronomers observed, identified, right, globular clusters. So globular cluster is basically like an agglomeration of many stars. It's like consists of 10 to the 5 stars. And if you have the disk of the galaxy, something like this, then the globular cluster usually sits, above the disk. It's not part of the disk of the galaxy, but it's above that. So they identified these globular clusters, and they were approximately 13 times 10 to the 9 years old. So, of course, there's a problem that if you have basically twice as the age of the universe, so they were, created a long time before the universe started, and that's a problem. So there was a first indication that maybe you need lambda to explain what you observe in the universe. But I think very convincing argument is this Nobel Prize argument, which I will discuss tomorrow, and then you will finish in your homework. Okay, so let me continue this argument tomorrow.